This lecture will go over Lewis structures of compounds, resonance structures, and formal charges. Now that we've learned how to name ionically and covalently bonded compounds, we're going to use what's called the Lewis theory to draw kind of abbreviated structures of them. It kind of helps us see how two elements bond. And the driving force, according to the Lewis theory, for making any chemical bond is that atoms tend to lose, gain, or share electrons, whatever they need to do to get a full outer shell of electrons, which is 8 valence electrons. So Lewis dot structures, also known as electron dot structures. As a refresher, I just want to remind you that all common ions lose either all of their valence electrons or gain additional electrons to get a full outer shell. And so, as we can see here, the metals lose all their valence electrons to become the isoelectronic with the nearest noble gas. And then the nonmetals will tend to gain enough electrons to also make them isoelectronic with the nearest noble gas. So Lewis dot structures uses dots around the symbol of the element, and the dots represent the valence electrons. Okay, so only the valence electrons. So as you know, oxygen is in group 6A on the periodic table. It has 6 valence electrons, and the general rule for drawing a Lewis dot structure is you put 1 electron on each of the 4 sides of the element before you start pairing them up. Okay, so you would portray oxygen like this. You would not, kind of like Hund's rule a little bit, you would not draw oxygen like this. And the reason this is more useful is by looking at this Lewis structure. Hopefully you can see that oxygen is most likely going to make 2 bonds because it has 2 unpaired electrons. So it ends up being a pretty useful theory. So here are the Lewis dot structures of several of the common elements in the periodic table. Of course, remember that helium is unusual, that a full outer shell for helium or hydrogen is simply 2 electrons, since they only have 1 electron energy level around them, and that first electron energy level is full, considered full, with only 2 electrons. Alrighty, so we can also use Lewis dot structures to show how a compound is made from individual atoms. So for example, if an ionic bond is being made, and so again, that would be between a metal and a nonmetal, right? And we know that metals have very low ionization energy and will therefore tend to give up or donate one of its valence electrons or all of its valence electrons to become a cation. And we also know that the halogens have a high electronegativity, and they will tend to gain extra electrons to become anions. And so that is how we show the formation of an ionic compound. And the arrows will typically show electron flow. The arrows will start at an electron-rich source, in this case the electron itself, and will point to the atom to which it's donating the electron, or to which the electron is moving. So what about drawing Lewis dot structures for covalently bonded compounds? A little bit more complicated. Now, ionic compounds, let me emphasize a couple things with them, is that cations in an ionically bonded compound are simply shown with no valence electrons, even though that we know underneath it has a full outer shell. It's given away its original valence electrons. So we show cations as having, I show them naked cations, no dots around them, okay? And the anion in an ionic compound quite the opposite is shown, because it accepted extra ones, is shown with the 8 valence electrons. So remember that, okay? That could be kind of a simple multiple choice question on an exam. So, all right, now let's shift gears and talk about drawing the Lewis dot structures for covalently bonded compounds, molecules. And there's several rules, and it can get kind of tricky because we have to worry about single bonds, double bonds, triple bonds, all sorts of things. So here are the basic rules. The first thing you want to do, if you're given a formula and said draw the Lewis structure, is add up all of the valence electrons for all of the atoms in that structure. So, and as usual, my PowerPoint didn't upload with all the format the way it should be, but let me see if I can point things out. Phosphorus has 5 valence electrons, and, ooh, I see what happened. That 3 should be a subscript, okay? The halogens each have 7 valence electrons, and of course there are 3 of the chlorines here. So the total number of valence electrons for phosphorus trichloride is 26. Okay, so that's the first thing you want to do is add up valence electrons. Now be careful, because if the structure has an overall charge, okay, so let's say we had ClO with a minus charge, okay? What does that minus mean? That minus means there's an extra electron, right? From normal, you've got to account for the sign. So in this case, let's see, chlorine has 7 valence, oxygen has 6, so you would say 13, but then you'd notice the negative charge and realize that means 1 extra electron. So in this case, that would have 14 electrons. So just pay attention to charges. All right, the second rule is you want to arrange all of the atoms and connect them to begin with just single bonds. That's just one line. Okay, now there's typically a central atom, and then there are outside atoms. The central atom is typically the first atom that is written in the formula. So PCl3, phosphorus was first. Okay. Another kind of rule of thumb chemists use is the first atom, and therefore the central, usually is the one with lowest electronegativity, or the smallest group number, I've heard it called too, okay? So anyway, you want to arrange the atoms with single bonds, and now you need to start counting the electrons that you've placed. Every single bond consists of 2 electrons. So you can see here we have used 6 electrons, okay? 2, 4, 6. We have to find a home for 26 electrons. So we have 20 more electrons to place. So just start kind of tracking them. Step 3 is give the outer atoms, so everything but the central atom, an octet, or 8 electrons. Keep in mind that each single bond already counts for 2, right? So you want to go ahead and fill in enough electrons on all of the outer atoms so that they have a total of 8, an octet around them. When you have done that, count how many electrons you've used total again, and you'll see that so far, since we have 3 outside atoms each with 8 electrons, so far we have placed 24 electrons. Remember, we have 26 to place. So we need some place to put the 2 electrons we have left over. Well, the next rule tells us if there are any electrons left over, after you give the outer atoms an octet, you put them on the central atom. So here are the 2 extra. And now if you count, we have placed 26 electrons and we are done. You don't want to just stop there, though. You want to make sure that all of the atoms in the structure are stable, and that's where the tricky part comes in. The first thing you want to look for is that every atom has an octet or a full outer shell. Keep in mind that hydrogen has a full outer shell with only 2 electrons. Just tuck that back. So let's see. All 3 chlorines have an octet. And now that we added these 2 extra electrons on phosphorus, it also has an octet. See, 2, 4, 6, 8. So that is a stable structure, and we are done. Now, it gets a bit more complicated, so I want you to make a note of the last part of what I have written on this PowerPoint, and that is that there are some elements that are capable and readily do expand their octet, which means rather than stopping at when it has 8 electrons, valence electrons around it, there are some that will hold 10, 12, and even 14 valence electrons. And they are typically elements that are farther down on the periodic table. So the general rule is if an element is in period 3, 4, 5, 6, okay, it will, or 7, as far down as you want to go, the larger elements can expand their octets. And the theory behind that is that they have D block orbitals that are close enough in energy to accept some extra valence electrons. So we'll do a couple of examples of those. Now, the last rule is, what if you run out of electrons and all of the atoms involved do not have an octet? What do you do? So let's look at example. What if I gave you just the generic formula this and said draw a Lewis structure? So you're going to count the valence electrons and say, okay, I have 10 valence electrons. Then you're going to start following the rules, right? So hydrogen can never be a central atom because it can only have one bond, not two. So carbon is the central atom. You're going to draw single bonds. And so far we've used 2, 4 electrons. We have 6 more electrons to place. So now we give the outer atoms an octet. Notice that hydrogen has a full outer shell with only 2, so you're not going to add any more to it. So we're going to put all 6 of the extra electrons around the nitrogen, which is great because now nitrogen has an octet, 2, 4, 6, 8. We're out of electrons. So this is where you have to get in the habit of asking yourself, are all of the atoms stable? Do they all have an octet? Carbon does not. Carbon only has 2, 4 electrons around it. That is not good. There's no way that Lewis structure is stable. So the final rule is if you run out of electrons before the central atom has an octet, you must start forming multiple bonds. And by multiple bonds, I mean double and triple bonds until the central atom has an octet. So let me show you how you do that. You're going to take one of the pairs of electrons on an outer atom, okay, in this case it would be nitrogen, and you're going to move those electrons over to make a double bond. So what happens when I do that? Let me draw that. So now you have what we call 2 lone pairs. These things are called non-bonding electrons or lone pairs instead of 3, right? And so now let's count valence electrons. So nitrogen still has 8, okay, and it won't change that, 2, 4, 6, 8. But what does carbon have now? We've made it a little better. It has 2, 4, 6. But carbon only has 6 valence electrons, so we need to go ahead and make another multiple bond. So we're going to do the same thing that we already did. We're going to take yet another lone pair, a non-bonding pair, and move it to make yet another multiple bond. And so the structure we're going to end up with is right here, whereas there's only going to be one non-bonding pair on nitrogen and a triple bond between carbon and nitrogen. Now you can see that all of the atoms involved have a full outer shell that's very stable. We've still only used our 10 electrons, right? This takes quite a bit of practice, all right? So make sure you get one of the practice worksheets and work through a lot of them. All right, here's just a summary of what we did. You're always going to start by counting the total number of valence electrons. You're going to connect all of the atoms involved with single bonds, and then you're going to start counting how many electrons you've used. Then you're going to give all of the outer atoms an octet. And I have somehow, must be in transferring here, so don't write an extra step for yourself that says if when you run out of electrons, if the central atom does not have an octet, you must make double and or triple bonds until it gets an octet. All right, so here is practice for you. And writing that a little bit easier to read. There we go. It's called acetylene. It's a nice fuel for a torch. So let's go through it. If you think you might be able to try it, go ahead and turn the video off. Give it a shot. Okay. So we have 2 carbons. Each one has 4 valence, and we have 2 hydrogens. Each hydrogen has 1 valence. So we have a total of 10 electrons again. Now, we know hydrogen always has to be an external atom. It can only make 1 bond, so I know hydrogens have to go on the very ends. Okay, they can't ever be in the middle. So how many electrons have I used so far? Each single bond has 2. I've used 2, 4, 6. Okay, so I have 4 more electrons I need to use. I cannot add any more to hydrogen. So what do I do with the extra 4 electrons? Let's see. I could put them all on 1 carbon, and then this carbon would have an octet, right? 2, 4, 6, 8. But then this carbon wouldn't have an octet. So what if I gave them each a pair? So 2, 4, 6, 8, 10. Is everybody happy? No. Each carbon only has 6 valence electrons around it. All right, so I am going to have to make multiple bonds. And so you might do this in steps, or if you have kind of a good intuition, you may be able to do it all in one fell swoop. Okay, so you may just try making a double bond, but then you would see 1 carbon has an octet and the other one doesn't. So the final correct structure for this is a triple bond between the 2 carbon atoms. So again, this just takes some practice, but it's not hard. You have to get used to it. Alrighty. So I mentioned that there are elements that can expand their octet, hold more than 8 valence electrons. There are 3 general types of exceptions to the octet rule. So one of them is you might end up with an odd number of total electrons. And we're used to pairing all the electrons up. But especially when nitrogen's involved, you often end up with an odd number, depending on how many nitrogens are in the molecule. So, for example, if you have neutral NO, okay, 5 plus 6 or 11 valence electrons. Okay, so you're going to have an odd man out, regardless of how you configure that. And so one of these 2 atoms is only going to have 7 valence electrons around it. You can write this both ways. Which way is the better way? Okay, so typically you need to consider if you have 2 resonance structures that seem really close to you, one of the things you need to consider is electronegativity of each atom. Electronegativity, hopefully you will remember, is the attraction for extra electrons. Okay, so as you go toward fluorine or over to the upper right of the periodic table, elements become more electronegative. They're more and more of a drive or attraction for extra electrons. So oxygen is more electronegative than nitrogen. It's closer to fluorine. And so oxygen has a much stronger attraction for electrons. Well, maybe not much, but significantly stronger attraction for electrons than nitrogen. So no way is oxygen going to be happy if it only has 7 valence electrons. So because of that, this first Lewis dot structure is going to be the preferred one because oxygen has all 8 electrons and nitrogen is the one that's shortchanged, but nitrogen doesn't put up as much of a fuss when it is shortchanged electrons. All right. As I said, there are some elements that will hold more than 8 valence electrons. There are some that are quite stable with less than 8 electrons. The most common, the ones that I want you to be aware of at this point, are beryllium and boron. Beryllium is content, believe it or not, with only a total of 4 valence electrons, and boron is stable with only 6 valence electrons. So boron trifluoride, for example, has 24 valence electrons. And so you would probably, if you followed the rules and didn't remember that boron is one of the exceptions, you might end up with a Lewis dot structure like one of these. But it turns out those are not stable, and how boron trifluoride exists in nature is simply like this, where the 24 electrons are spread evenly around the external fluorine atoms, and boron in the center only has 6 valence electrons, and that is the most stable configuration. As far as beryllium, you could easily see molecules like this, where beryllium only has 4 valence. So that's just something you have to memorize. And the third exception to the octet rule is the one that I mentioned earlier, and that is there are some elements that can hold more than 8 valence electrons. And those elements, any element in the third, fourth, fifth, or sixth period on the periodic table, so the bottom, essentially the bottom half of the periodic table, those elements are capable of expanding their octets and holding more than 8 valence electrons. So this compound, for example, is phosphorus pentachloride. As we get into larger or more complex covalent molecules, you're going to find that you're often able to come up with 2, 3, and even 4 possible Lewis dot structures. And so it's very important that you understand how to determine the best or the most stable Lewis dot structure. And so what we use is to be able to choose the more stable structure is formal charge. So the first thing I want to emphasize is formal charges are not actual charges. So when we talk about cations and anions and ionic molecules, we have a fully developed charge. Formal charges, it's really a bookkeeping method for trying to track and see where valence electrons from individual elements have gone, like if they've been kind of donated or so it's really kind of a bookkeeping method for valence electrons and bond making. It is not a full charge. Please remember that. All right, so I'm going to go ahead and tell you how I find formal charge, and then I'll go ahead and give you the textbook definition too, and then whatever method works for you, great. So formal charge is basically the number of valence electrons that an atom has on its own, okay? Number of valence electrons an atom has when it's on its own, so that's just from the periodic table. Okay, minus the number of valence electrons that atom has when it's in the compound. And I'm going to give you examples. Okay, so the number of valence electrons an atom has on its own when it's not part of a compound, minus the number of valence electrons that same atom has in the compound you're looking at. So let me give you an example. Let's do this oxygen, okay? So oxygen is in group 6A, so it on its own has 6 valence electrons. Then you have to ask yourself, how many valence electrons does oxygen have in this compound? Well, the lone pairs belong only to oxygen, so each non-bonding or lone pair belongs to oxygen exclusively. So that's 2 plus 2, that's 4. Then if you're talking about bonds, oxygen can only claim one of the two electrons in each bond. So there's a double bond, so it's going to claim one of the electrons in each of these bonds. So in the oxygen in this compound has 1, 2, 3, 4, 5, 6. Okay, so oxygen has a formal, in this compound, has a formal charge of 0. Now let's look at the other oxygen. Again, oxygen has 6 valence electrons when it's on its own. In this oxygen, in this molecule, has 2, 4, 6, and one of the 2 electrons in the one bond, 7. Okay, so it has 7 in this. So this particular oxygen has a formal charge of -1. Let's do the nitrogen. Nitrogen is in group 5A. It is an atom on its own, has 5 valence. How many valence does it have in this compound? Well, it gets both of these for the lone pair, and then it gets 1 electron from each bond. And there are 1, 2, 3 bonds. So it has these 2 plus 3 more, so 5. All right, so nitrogen also has a 0 formal charge. So let me I'm going to redraw that since I'm very good at making messes. Okay, so if I redraw that, and I've drawn this so much I just remember what the Lewis dot structure is, but you can always draw it for yourself and prove it to yourself. Now it turns out this is a polyatomic ion, NO2 minus. There is an overall charge of -1. What I wanted to point out here is the sum of the formal charges must equal the overall charge of the compound. And they do here. So if you remember, we said this oxygen has a formal charge of 0, nitrogen has a formal charge of 0, and this bottom oxygen has a formal charge of -1. So the formal charges do all add up to -1, but just make sure when you're done that they do. Now, there is another example at the bottom of the page. Let's look at carbon dioxide. Alrighty, so the original valence electrons the atom has on its own, that's what all these top rows are. And then the number of valence electrons that the atom has in the compound. Once again, count the lone pairs, the non-bonding pairs, count all of them, and count only 1 electron from each bond. All right, so this oxygen has 6 even in this compound. It's got a formal charge of 0. So does carbon, right? Now, these are 2 Lewis dot structures that you could draw for carbon dioxide. And you might not know, unless you knew formal charges, which one is preferable. But now that you hopefully will remember to do formal charges, if you come up with more than one Lewis dot structure, you can see that the structure on the right, the oxygen to the left has a formal charge of -1, and the oxygen to the right has a formal charge of +1. Now, the whole idea is to minimize formal charge. So if electron distribution, the more stably, the more evenly it's distributed throughout a compound, the more stable the compound is. And we know that by minimizing formal charge. Okay? So if you can get a structure where none of the elements have a formal charge, perfect. If you have to have a formal charge, if all the Lewis dot structures have a formal charge, pick the one that has the lowest values. In other words, +-1 would be better than +-2. Okay? And here is the textbook definition for calculating formal charge, in case that works better for you. I have just found that kind of confuses me, and it has confused some students in the past. All right. I have talked about the idea of coming up with multiple Lewis dot structures, and it turns out those are called resonance structures. So if you come up with more than one Lewis structure that has followed all the rules, you've used all your electrons, atoms have octets, those are resonance structures. And so really a resonance structure, just the only difference between resonance structure is the distribution of valence electrons. Okay, so arrangement of atoms is the same. You always have nitrogen, then carbon, then oxygen. So if I wrote nitrogen bonded to oxygen bonded to carbon, if I change the order, that would not be a resonance structure. So again, a resonance structure only has different arrangement of the valence electrons among the atoms. So again, you want to minimize formal charge. And the secondary thing you want to keep in mind after you've looked at formal charge is you want to make sure that the formal charges are on the appropriate electronegative atom. So, for example, oxygen is more electronegative than nitrogen, right? So, oxygen doesn't want to end up with a positive formal charge. It's just not going to be stable that way. Okay, so keep that in mind. So let's look at this specific example. We can pretty quickly rule out the first structure because the absolute value of the formal charges is high. Okay, you've got a formal charge of 2 here and you don't on the last two. So the last two, your total formal charge is -1, and then 2 out of 3 atoms have 0 formal charge. How do I pick which one is best? Well, in the middle case, the nitrogen has a formal charge of -1, and in the right-hand case, the -1 formal charge is on the oxygen. As I said, oxygen's more electronegative, therefore has a stronger attraction for extra electrons and negative charges, and so that is where that -1 formal charge, even though it's not a fully developed charge, it does give us information about the distribution of the shared electrons. So that is the one that is the most stable Lewis dot structure. So they get pretty tricky, so you practice them. All right, here is, I thought it would be good to put one kind of high level example in here. Let's draw the most stable Lewis structure for SO2. Okay, and let's go through all the steps. So the first thing you want to do is count valence electrons. Sulfur and oxygen are both in group 6A. So you have a total of 18 valence electrons. First step, draw single bonds. S comes first in the formula, so we're going to use that as the central atom. Second step, give your outer atoms, in this case oxygens, an octet. How many electrons have we used at this point? That's 8, and that's 8 more. We have used 16 electrons. We have 2 more electrons to place. The next rule says that extra electrons go in the center atom. Now, probably a third of students would stop here on an exam, but you have got to remember this rule, so highlight it, okay? Make a really big deal out of it. When you do the first 4 steps, do all the atoms have a full outer shell? Do they all have an octet? No. Okay, sulfur only has 6 valence electrons here. 2, 4, 6. It's not stable. It wants an octet. So at this point, you must make double bonds. Okay, so remember how to do that. Both oxygens are equivalent here, so just pick a non-bonding pair from one of the oxygens, move them over to make a double bond, and then recheck. Does your sulfur have an octet yet? Yes, it does. That's 4, 6, 8. So you are done. Okay. Now, a problem may well ask you, even though there's not more than one, well, there would be another. Let me show you something. And that last slide, I think, goes over this, but I'll just introduce it. What's the difference between what I have written there and this? All I've done is switch the places of the oxygens, right? The double bonds with one oxygen, and over here it's with the other one. These are called equivalent resonance structures. In other words, you can't pick one as more favorable over the other by formal charge because they're essentially equivalent. Equivalent, I can't talk anymore, resonance structures. Okay. All right, so we're going to go into that in the last couple slides, but you will likely be asked to figure out the formal charge on each atom. So make sure you can do that, practice. You'll learn pretty quickly that in general, oxygens with just a single bond typically have a formal charge of -1, and oxygens with a double bond typically have a formal charge of 0. So now let's look at sulfur. We know sulfur starts out with 6 valence electrons. In this particular structure, it has 2, 3, 4, 5. So sulfur has a formal charge of +1. Right? So SO2 overall is neutral. Okay, there's no charge overall. And so the formal charges better add up to be 0. And they do, +1, -1. So everything's good there. There is a glitch or a catch. Even though everything seems perfectly fine with this Lewis dot structure for sulfur dioxide, it turns out that when you study it more closely, the actual structure for sulfur dioxide shows 2 double bonds, one on either side of the sulfur. So let's explain what's good. This is probably the highest level of Lewis dot structure that you're going to encounter in this course. So if you can grasp this and repeat this, that's good. That's what I would expect from my A students. All right, so since you do have formal charges, remember we had a -1 on this oxygen and a +1 on this sulfur. If the central atom can expand its octet, and sulfur can, okay, it's in period 3, so anything in period 3, 4, 5, 6. If by expanding its octet you further minimize formal charge, the compound will do that to stabilize. So let's play with that idea. All right. Let's see if we take another non-bonding pair from the other oxygen and we use it to make another double bond. Let's now check formal charges with this structure, and we'll move down here where it's not as messed up. All right, the formal charge for each of the oxygens now is 0. Okay, they each 2, 4, 5, 6, and they start with 6. Okay, remember sulfur had a +1 formal charge in the original Lewis dot structure. Okay, sulfur starts with 6. How many does it have here? 2, 3, 4, 5, 6. Every single atom in the structure now has a 0 formal charge. But how many total valence electrons does sulfur have around it? We have now expanded its octet, and we're not counting valence electrons for formal charge. Now we only count half of the bonding ones. We're counting them total to see what it feels around it. 2, 4, 6, 8, 10. So now sulfur has a total of 10 valence electrons around it, so it's expanded its octet, but by doing so, it's minimized the formal charge and is more stable. Alrighty, I had mentioned equivalent resonance structures before, and ozone is another example. So just be aware that's what that's called in case you're asked a question to do with that. When you end up with a most stable Lewis dot structure and you notice that you can move a double bond around from one side to the other, sometimes there are 3 equivalent structures depending on how many equivalent bonds there are. And be able to draw equivalent bond structures. Now, the last little bit of information I want you to understand when you have equivalent bond structures is what you call the bonds, okay? So the actual structure of ozone is a hybrid, okay? It's a mix. So this double bond does not go back and forth between two oxygens and then another two. It lives its life somewhere in between. And how chemists tend to show that is with a dotted line. Okay, so they kind of do this to show that there's a double bond that's distributed among three oxygens. So looking at just one of these resonance structures, you would say, okay, there's an oxygen-oxygen double bond, and there's an oxygen-oxygen single bond. Okay, but if you average 1 plus 2, right, and you average it, what are you going to get? 1.5. So what we say is that the bond order, that means how many bonds are there, one, single, double, triple, the bond order for oxygen, oxygen, and ozone is 1.5. So if you have a single bond like this, you would say the bond order is 1. That just means there's a single bond. If you have a double bond, you would say the bond order is 2. All right, and a triple bond, the bond order is 3. Where it gets tricky is when you have these equivalent resonance structures and you have to take an average. I feel like I have probably used your brain cells, exercised them enough, so that is the end of this PowerPoint.